All right, let's dive right in. Welcome to today's Explainer. Now we're going to be looking way past a recent viral headline about a vulnerability called copy fail. We aren't just here to look at the bug itself, we're actually going to uncover a profound systemic shift in cybersecurity that's hiding just beneath the surface of this whole story. It's a shift that completely changes how we think about code, safety, and literally the future of our digital infrastructure.
732. I really want you to just let that number sink in for a second. That is the exact byte size of a Python script that recently sent absolute shockwaves through the tech world. Think about it. It's shorter than a standard paragraph, yet it somehow managed to compromise the world's Linux servers in a matter of moments.
Because with just those 732 bytes, and we're talking standard Python libraries here, no compiled C, no crazy custom tweaks, an unprivileged user can become root on essentially every single Linux machine on Earth shipped since 2017. We are talking about the whole shebang, from the GPS satellites that guide your phone to hospital imaging systems, right down to the AWS instances hosting the company you work for. All of it, subverted by one tiny script.
So what exactly is copy fail, or officially CVE 2026-31431? Well, it is not some loud, noisy denial of service attack. Your servers aren't going to crash. Instead, it's a stealth privilege escalation. It basically takes a janitor account on a shared server or a CI runner with the lowest possible permissions and hands it absolute root access by silently manipulating memory. And the truly terrifying part, it leaves absolutely no forensic trace on the hard disk. None.
Let's look at the anatomy of a time bomb and see how 3 completely innocent commits broke Linux.
We really need to unpack the technical mechanics here, because this wasn't just a single catastrophic mistake dropped in by a bad actor. It was a time bomb built piece by piece over 6 years. It started in a niche corner of the Linux kernel called the AF_ALG socket family. In 2011, a cryptographic mode called authencesn was added. It harmlessly borrowed 4 bytes of private kernel memory for scratch space. Perfectly safe, right? Then, in 2015, 2 updates allowed user apps to hand the kernel page cache pages, which are just in-memory copies of real files on your disk, using the splice system call. Still, no explosion. But then came the fuse in 2017. A totally sensible performance optimization that made cryptographic operations happen in place to save memory. It explicitly set the source buffer equal to the destination buffer.
And that right there is exactly how the 200-millisecond exploit is crafted. Because of that 2017 change, the script opens a secure root binary, splices its page cache into that AF_ALG socket, and triggers the crypto operation. The kernel, going right back to its 2011 habit, deterministically overwrites 4 bytes inside that in-memory binary. Those corrupted bytes alter the binary's instructions, handing control over to the user's code. Boom! The user gets root access, exits cleanly, and the system just drops the corrupted memory like nothing happened.
Now check out this contrast, because this is the part that literally keeps security pros up at night. On your physical ISK, the binary is completely untouched. It passes every single integrity check, SHA-256, MD5, you name it. But the in-memory binary, corrupted, overwritten with those 4 tiny bytes, granting root access to anyone who runs it. This silent, memory-only manipulation is a real game changer in the worst possible way.
Which brings us to the bug hunter and the actual truth behind this discovery. Okay, here comes the massive plot twist. Who, or really what, actually found this 9-year-old bug? Just think about this brutal math for a second. On one side, you have 9 years of thousands of human eyeballs auditing the Linux kernel, which is arguably the most heavily reviewed open-source software on the planet. On the other side, 1 single operator prompt and roughly 1 hour of AI compute. The traditional manual open-source review process missed this entirely for nearly a decade. Yeah, this bug wasn't found by Google's Project Zero or some elite team of pen testers. It was found by an AI, specifically a product called Xint code from a security firm named Theori. They gave their AI a single, super vague prompt. Just scan the Linux kernel's crypto subsystem. No custom rules, no breadcrumbs. About an hour later, the AI spits out a highly confident finding that turned out to be this absolute nightmare of a vulnerability. So why did AI completely crush it here while humans failed? Well, copy fail is what we call an integration bug. That's a logic flaw emerging from multiple, separate, completely non-malicious code changes stacked over years. Humans are catastrophically bad at holding 6 years of disconnected commits in their heads simultaneously. Actually, scratch that. It's virtually impossible for a human to spot a contradiction like that once the original authors have moved on. But large language models with massive context windows, they excel at it. They don't forget what they read 3 years ago, they just see the contradiction instantly.
This leads us to the broader AI trend, proving that this is absolutely not an isolated incident. If you're thinking, okay, maybe copy fail was just a crazy fluke, let's zoom out a bit. In November 2024, Google's Big Sleep AI found a memory safety bug in SQLite. Right after that, Google's OSS Fuzz paired with AI uncovered a 20-year-old out-of-bounds bug in OpenSSL, the library that secures practically the entire internet. And just before copyfail dropped, Anthropic's Claude Mythos preview was autonomously identifying 0 days across major operating systems. The metabolic rate of the security industry has permanently shifted.
Let's talk winners and losers and the shifting economics of cybersecurity.
Whenever you have a paradigm shift this massive, there's going to be economic fallout. On the winner side, you've got Theori and basically the whole AI security vendor space. They just got the ultimate proof of concept to end any corporate procurement debates. The Linux ecosystem also wins in the long run by getting a significantly safer kernel. But the losers? Well, the manual pen testing industry is definitely going to face some severe rate card compression. The Red Hat Enterprise Linux ecosystem, famous for its conservative patching cadence, is now sitting on a huge liability. And the classic open source mantra of Linus's Law, the idea that more eyeballs make all bugs shallow, takes a pretty huge credibility hit, because human eyeballs simply don't catch these complex integration bugs.
For years, decades really, sysadmins have lived by the golden rule. If it ain't broke, don't patch it. Constant patching is expensive, it's disruptive, I get it. But here is the hard truth. That infrastructure model is now completely obsolete. Running a rock-solid, stable 2018 vintage kernel is no longer a safe bet. It's an active, highly exploitable liability.
Welcome to the new arms race, defined by a terrifying speed mismatch between attack and defense.
To understand what's happening, we need to look at how things used to work. For 30 years, we've relied on this classic 4-phase vulnerability lifecycle to keep everything safe. First, discovery, which usually took months, sometimes years. Then you have coordinated disclosure, followed by patch development, and finally, that incredibly long tail of customer rollout. It was a slow, patient dance, built entirely around human speed.
But here's the massive speed mismatch we're dealing with today. Attackers have weaponized AI to compress that first phase, discovery, from months down to mere hours. Yet the human defense pipeline, the disclosure, the patching, and the enterprise rollout, is still stuck ticking weeks or even months. The fast end of the pipeline keeps getting exponentially faster, while the slow end is just staying completely static.
Just look at the chaotic timeline for copy fail. This shows exactly how fast weaponization happens now. The kernel patch quietly landed on April 1st. Public disclosure hit on April 29th without any prior warning to distribution maintainers at places like Ubuntu or Red Hat. By May 1st, CISA had to order mandatory federal patching, and within under 48 hours of that, mass exploitation in the wild by ransomware groups. When the barrier to entry is just copy-pasting a standard Python script, the bad guys move insanely fast.
And it all boils down to this core structural asymmetry. Think about it. An AI scanner is just one single tool in a defender's long pipeline of testing, triage, and patching. But for an attacker, an AI scanner is their entire weaponization pipeline. Defenders still have to win every single fight and fix every single bug out there. Attackers, supercharged by AI, they only have to win once.
So, what about the future? How do we actually go about surviving the AI vulnerability era?
Look, what worked in the past is simply not going to protect us tomorrow. To close this insane gap between AI discovery speed and human deployment speed, organizations have got to adapt right now. We need to fully embrace automated patch deployment. We need to implement AI-assisted code review directly at the maintainer level before code ever merges. We have to fundamentally rethink our merge processes to catch these multi-year integration bugs. And yeah, we absolutely need to adjust security budgets to include automated AI scanners on the defensive side.
So, I want to leave you with a pretty stark question. How does your organization plan to survive in a world where the attacker only needs to win once at AI speed? The reality we're facing is that the discovery side of cybersecurity just sped up by an order of magnitude. It is time to make sure your deployment side catches up before your systems become the next cautionary tale. Thanks for joining me for this explainer, and keep learning.